just the arrow. So let's see what the arrow does. So what I mean to say by that arrow is basically whatever we're putting it as input, after applying the weights and biases, we get, and whatever that output is, we'll be passing it back into itself along with the next input. So what that would do is give it a sense of what came before it. So think of it as having information about the previous output, previous input. So let's try to unroll this neuron over time. Now here's why the word time is important, because these two neurons are the same neurons. In one, the neuron in the next time step would be the same neuron as this neuron. So we'll come to that later. So now let's imagine that I have a, let's say I have a sentence. Let's say I have a sentence of 3 words. Let's say I am an. Okay, let me try to write this. I'll change the presenter mode. Just a second. Yeah. So okay. So now I can write stuff on it. So so right now let's say I want to write on this. So let's say I have a word. I have 3 words which I want to pass into it, and I want to get a prediction out of it. So just like we did our sentence thing, like we had 4 words and we wanted to predict the 5th word. So if I want to do something similar with this, what I would do is, let's say I have 3 words: I am an. So now, so now I have 3 words, and now I want to predict like the next word that could possibly come in this. So let's think of this as the first time step. So it could be anything. It could be t equals 1, t minus 1. You can understand it as however you want. Just know that this is the first step in our this is the neuron in our first step. So what we'll do is we'll basically take in the first input, pass it in, and then it will apply its weights and biases, and we will get an output over here. So now this is a time step. So this is one step. So now let's go to the next step. So now over here, what we will do is now we want to pass in am, right? Because we want to make a prediction based on these 3 words. So once I pass in am, if I just pass in am on its own, it will have no idea of what came before it. So therefore, instead of just passing am, we will also pass in the output from the previous step. So that's what this arrow signifies. So this output basically contains information about the word that came before this input, about the input that came before this one. So basically, this output contains information about I. And now this neuron right here has the information about this new input, which is am, as well as the previous input, which was I. And how does it have that? Because it got the output from the previous step. Do again keep in mind, it's really important to understand that this is the same neuron, but just 2 times. These are 2 different time steps. The only thing that's changing is the input. The neuron is the same. If this neuron has the name Bob, this is also Bob. This is the same Bob all the way. Okay, the neuron isn't changing. That is very important to understand, that this is the same neuron. Just the inputs and the outputs are changing. So okay, we don't need this anymore. Okay, yeah. So now coming on to the third word, which is the an. So if we go in the next time step, uh, yeah. So if we go to the next time step, we want to put in the word an. So we put in that word, and along with it, we get the output of this time step t. So what that output contains is the information about input at t, which was am, as well as input at I, which was input at t minus 1, which was I. So as this guy had the input of both of these, this guy would also have the same input as a form of output from this guy. So right now, this neuron right here, this step, the neuron at this step, Bob, at this step, has the information about the input at t, which was am, input at I, which was I, sorry, input at t minus 1, which was I, as well as the new input which you're putting an. So it has the input, it has the information of all 3 now. So now we don't want to add more information to it. We just want to now predict something out of it. So instead of mixing them and passing it on to passing it on to the neuron again, we will be trying to get a predicted output out of it. So how we will do that, we'll look at in the future. But just to complete this example, if this was my if this was my neural network trained on me, this would probably predict something like I am an idiot. So, so that's majorly because we used an over here, which symbolizes that the next word has to be started by a vowel. If it was it would have probably predicted something else. So all self-deprecation aside, so let's try to understand this better with the help of also, we can create like layers with these neurons. So like now we just saw that it was just a single recurrent neuron. We can create layers with this just like we create with our normal neurons. So this is an ANN with 3 neurons, and this is the RNN with 3 neurons. You know the same. You know why we have these arrows here. Basically, we keep getting the output from this and putting it back into itself. So let's move on. Uh, let's go deeper with the help of Jamboard. So I hope you guys know what Jamboard is by now. It's basically a whiteboard, but for your online classes. It's whiteboard COVID edition. So, okay. So over here, I've turned our circular neuron into a square or a box. Why, you may ask? Why have I turned this into a box? So basically because the box has 4 sides and our neuron has four inputs and outputs, like 2 inputs and 2 outputs. So I think I've done a good enough job of explaining what those 2 inputs are. So can you guys let me know in the chat what those 2 inputs are? If we talked about this, like one is the input that you're going to give at that time step, and what is the other one? Let me know about both of those input in the chat. Okay, Tanmay gave a pretty good answer. Okay, someone is making memes now. Yes, okay, yeah. Okay, so I'm guessing, so at least, I don't know, 4 of you guys understood. So I'm happy with that, I guess. So, okay, so let's give some denotation to these inputs. So one of them is like you guys mentioned the input at t. So the new input, so we'll denote it by x, let's say. Wow, this is a very interesting x. So let's denote it by x of t because it's at time t. So so I think it goes without saying that you'll have to pardon my handwriting because I'm using a mouse. It won't be any better with a pen, but just in case that someone gets offended about my bad handwriting. So now that was the input that we'll be getting at this time step. And the other input we were getting was the output from the previous step. So let's denote that with the help of theta. So like I said, you can think of this input as having the information about the previous step. Okay. So we'll be making the similar output for this neuron as well. So we'll get to that in a bit. But this was from the previous time step, so we have to denote it by t minus 1. That specifies it that this was from the previous output, sorry, previous time step. So now this also gives out 2 outputs. If you remember, so like I said, this theta is considered as having information about these inputs. So the theta at t, which we will be getting out from here, which will be passed into the next step, theta at t will have information about xt and theta t minus 1. So this will be the one which will be passing on to the future as a next step. And there will be another output y, which we'll be using to make some predictions. So basically, you can think of it as theta as having the information about these two, and by applying some weights to that information, you can make a prediction which will be sent out as y. And of course, this y will also be at time t. Okay, I hope that much is clear. Of course, feel free to ask questions whenever I have my chat open in the side right here. So I'll be able to look at it immediately. So yeah. So let's not try to fill in the middle part. Let's try to fill in what's going on in the center over here. Like it's not magic, right? There should be something that's going on inside it. So boom, okay, wow, what happened? Okay, everything is filled in now. So let me try to explain what happened. So we can't just get in the input, then add them and put it out as output, right? We need some weights, and with those weights, we need some biases. So I'm not going to go too deep into biases. It's just, I mean, you can if you want, but I won't be adding them here. But it's there. Okay, just understand that it's there. So here's our input at x of t, and we'll be multiplying it with the weight, let's say w. And then here's the output from the previous step at theta of t minus 1. And we'll be multiplying it with the weight of w naught or w0. But I won't recommend using w0 as it could get confusing. So it's w naught. So you can think of some, and use by doing that, by mixing these two in some way, we will get the output at theta t. So this is the output. The thetas are something that we are not actually getting out. Like we are not taking those out of here. We're not taking them out of the neuron. These are something that is being passed within the neuron itself. So you can think of these as some hidden state output. Just like the middle layers in our neural networks are called like the hidden layers. Similarly, this output can be called as a hidden state output. So to create this hidden state output for this, it has some information about, it has some combination of xt and theta of t minus 1 multiplied with their weights. But if we want to get a prediction out of it, and if you want to, so you can think of the thing that mixes these two as like a layer inside of the neuron, which mixes these two by adding weights to it. And then if we want to get a prediction out of it, we will be adding some more weights to this theta t, and then we'll be outputting it as y of t. So we'll be writing some equations now, but let's just look at first how the forward propagation takes place in our RNN. So now we're going to be going back to the circles now. Okay, boom. Now we have our circles. Now, okay, question time. Okay, before we go into questions, I think this is this. So every single one of this is the neuron. So the circles now our neuron is in a circle. So now this is not just a neuron. Let's consider this to be a layer of neurons, the recurrent neurons. So now you say every circle is the neuron. So now, and these are the different time steps. So as you can see, it is going across time. And let's say I have a sentence of 4 words. So, and those 4 words I'm passing in one by one as x1, x2, x3, and x4. Right? Hopefully that's not too confusing. And then we will be at the 4th word, we want a prediction as the 5th word. So for the 4th word, after passing the 4th word, we'll be getting an output y4 out of this. And we'll be passing it into the dense layer to get the final prediction out. So because like you saw in the CNN as well, that that after adding all your convolutions, after going through all the convolutions, you flatten the image and pass it into a dense layer. So similarly, you have to do the same things over here. So this is the dense layer right here, and you get the final output as y hat or y cap or whatever you guys want to say. So let's now, so this is our neuron L. Okay, or if you guys prefer this is Bob. Okay, this is our neuron Bob. Layer Bob. So now, can you guys tell me what would be the weight? So now these are the weights which we just discussed right now. So the weight for the for the current input would be W right here, which we have written here. Then the weight for which would be applied into the previous output would be W naught. I should actually written it here. So that's W naught. So, but we'll be looking at this one. So yeah, so that's W naught. And the weight which we will be multiplying it with the output will be WY. So right here. So can you guys tell me what would be the weights for this step? This step over here, what should I write the weights? Actually, yeah, it's back here. But yeah, what should I write to be the weights of over this steps for x2 and to get theta 2 and to for y2? Okay, give it to me in this order. What should be the one for x2? What should be the one before theta 2? And what should be the one for y2? Okay, then myself same weights. Okay, anywhere else? Any more guesses? Okay. Okay, so let's come back to a few minutes ago where I told you guys that it's very important to remember that this is the same neuron. That's the most important part, because I said that's the reason I said that is because the weights will remain same. The only thing that's changing is the inputs and the outputs. The weights are the same because it's the same neuron. We are just looking at it in different points of time. That means it's the same neuron, therefore it will have the same weight. So W naught here, WY here, and it will go on till here. So let's put one here as well, WY, W naught. Okay, so let's look at the second time step here and try to write some equations for it so that we can understand the forward propagation. So how the forward propagation is are happening, I explained to you in the PPT, but just for a quick recap, we're putting in x1 as the first word, then we're adding some weight to it, and then we're getting a hidden state output. We're passing it on to the next step. Now then we're putting in the new input x2 in the same neuron. That is again very yes, inputs, yes, Nisrin, inputs are different, but the neuron is the same. We're passing it into the same neuron. Keep that in mind. That's why the weights are going to be the same. The weights are the property of a neuron rather than the input. So in the next step, we'll be passing in x2, and along with x2, we'll be taking in the theta 1, which was the input from the previous step, or output from the previous step, and we'll be mixing those two. Then we'll be creating theta 2, which will be passed on into the next step. That will be the same neuron. So keep again, I cannot stress that enough. It's the same neuron, same layer, whatever you want to think of it as. So let's keep layer for now. So okay, so let's look at the time step 2. So I think we're at a position where we can write an equation to get this theta 2, which is one of the outputs based on x2 and theta 1. So in this case, we are trying to predict the word after x4. That means we don't really need this prediction outputs from the other. Okay, I should actually use the red pen. Yeah, we don't actually need the outputs from these other steps because we only want it after the word 4, which is over here. That's why we only done that, only at y4. So let's just look at time step 2 and try to figure out how we got theta 2 with the help of x2 and theta 1. So let's write this theta 2 equals, so let's say we get x2 and then we multiply it with some weight of w. Okay, then we add it with the previous output, which was theta 1 in this case, theta 1, and we multiply it with some weight w naught. And then we have to apply an activation function to it. I hope you know why we apply activation functions. So this activation function is usually rectified linear unit, ReLU, or tan h. So I don't go too deep into why that is, just know that it is. Okay. So of course, and then we can write a generalized equation for this. But let's also look at how the y4 is coming out. So the y4, so in this case over here in the last one, we will also have the theta 4 output, but we won't be using it for anything. We will just be using the y4. So now let's see how we got the y4. So y4 is equal to theta 4, which was the hidden state output from this, which we haven't used anywhere, just we using it just to get theta 4. Sorry, a y4. So theta 4 into wy. So this will literally, that's just it. That would give you the output for on which you can predict stuff, which you can send out to your dense layer and then predict stuff. So of course, this will also be activated by some other function. This usually is, I think, softmax. Yeah. So okay, so what happens? So you saw the equations related to how you get the outputs and the final output in which you can do your predictions on. So I think we can write like a generalized equation for this. Like instead of having theta 2 x2 theta 1, we can use the term t and write them in the terms of that. So now you'll be blessed by getting rid of my horrible handwriting. And over here, I've already written those generalized equations. So if you want to like make notes or something, go ahead. So the theta t, which is the hidden state output at this point, will be activated function of xt, which was the input at this time, times the weight plus the previous output, which was theta p minus 1, times this weight. And similarly, the generalized equation for yt would be an activation function of theta t, the activation function applied to theta t, theta t, which was the hidden state output of this stage, times the weight wy. So now that was how the forward propagation takes place, and these are the equations related to it. Now let's talk about back propagation. Now this is where a lot of people get confused. So we're not going to go too in depth into this. I'm not going to go too deep into this. but I'm going to let you know how you can how you can find out the weights and biases based on backward propagation. So if you guys, I'm sure you guys know what backward propagation is, but just a quick revision that backward propagation is nothing but we go back through the steps that we came forward and we just go on updating your weights so that the loss function that we calculate is the minimum, okay, with respect to that weight. So, okay, let's come to this example. So I just copy pasted this entire thing over here. It's a bit smaller now, so I don't think it's that like not visible or something. Uh, so over here we have our predicted output y hat. So, and if this is a if we have a testing data for it, then we also know the actual value of y that should be there. So our loss function would be a function of these two things. Like how we calculated it, I'm not going to go too deep into it. Like what exactly is in the function, because the loss function for recurrent neural networks is a bit complicated, and I'm not going to go too deep into that. So the loss function, I'll just denote it by L, would be a function of y and y hat. So this loss function is the thing that we want to minimize with respect to the weights. So let's say, so in this case, we have three weights. So one we have wy, one we have w naught, and one we have w itself. So how do we do this? So instead of thinking of this as three separate weights, sorry, three weights in a single layer, you can think of it as an individual layer having these specific weights. So for example, you got this y. Think of it as you got this y by three separate layers having these weights each. So you got this from a layer and it had the weight wy, and you got this from another layer and it had the weight w naught, and also another layer which had the weight w. So this actually simplifies the way you backpropagate, and you can actually update the weights a bit easier with this. So for example, if you want to update wy right here, so you can see that wy is directly related to y hat because it's being passed on. So if you want to calculate the dou L by dou wy, so a simple way to do this would be uh, dou L by dou y hat multiplied by dou y hat by dou w y. So that's how you can calculate dou L by dou y, and then to update this weight, you will just be doing wy equals. So this is using chain rule, by the way. So yeah, so wy will be wy minus this dou L by dou wy we got. So similarly, you can carry out these steps for W as well as W naught. Let's look at the one for W, and then we'll go on to the next one. Because I'm not going to be going too deep into this, so it's really not that worth it to go and go through every one of those weights. So let's look at the dou L by dou W. So you can see that W is related to theta 4, and then theta 4 is related to y hat. So because it's related to y4. So over here you can see that it would be something like, sorry, W is related to y4. I'm so sorry, not theta 4. So dou L by dou y hat multiplied by dou y hat by dou y multiplied by, okay, pardon my handwriting. I hope you are getting what I'm trying to write. Dou y multiplied by dou y by dou w. So that's how you backpropagate. You can do it similarly for W naught. So if you have to go one step back, there will be more variables in here. And yeah, that's how you backpropagate. Now over here, you can see that this is a very specific architecture, right? I have given this guy 4 words and I've asked it to predict the next one word. So there is multiple other iterations of this. Also, I forgot one more thing. I actually checked the Q&A right now. What would be the value of theta 0b? So if you guys can you guys try to answer this question? So right here we took the example for x2, right? And over here we took in x2 times w plus theta 1 times w naught. So what would be the case for theta 1? So like for example, if it was theta 1, it would be g times this plus theta 0, right? Theta 0 times w0. So what would our theta 0 be? So if we have theta 0 here, what would the value of theta 0 be? Can you guys let me know at the chat? Like, what do you think it could be? Okay, Gaurav gave an answer. Okay, 1, okay. Okay, so I'm going to tell you, like, it's something that it's not like guessable. So yes, it is 0 because we don't have anything there, right? We can't assume it to be anything because 1 could be something that we get as an output, but 0 cannot be the case because we'll be using biases. I have not written biases here, but it won't be a case. 0 won't be a case. So that's why we'll be passing 0 as a starting, because that way we will know that there was nothing before this. So that's why the first one that we pass is just a 0. There is no, yeah, I mean, yes, that's because it's 0. That's why there is no theta 0. But if we write the equation for theta 1, there is a term of theta 0 based on the general equation right here. So yeah, it will be 0. So it will be solely based on the current input that you've given it. So that's it. So now where was I? I was saying that this. So we have given it four inputs, like 4 words, and we asked it to predict the fifth word. So that is one of the many architectures our RNN has. So one is the one that I just told you. We given 4, we asked for 1. That is the many to 1. So now let's go back to our PPT and we'll check out the